So far, in calculating accelerations and forces in bodies, these Newton's second law problems that we've done, all of the forces we've dealt with have either been along the line of motion or perpendicular to the line of motion. And so the forces that are along the line of motion have contributed, have gone into Newton's second law for calculating accelerations, and the forces that are perpendicular have not affected the motion, not affected the acceleration. But what happens when the forces are in between parallel and perpendicular, when they're at some angle? So that's what we're going to do here. This is when forces are not purely parallel or perpendicular to the line of motion. And what we're going to do in this case is figure out the components of those forces that are parallel to that motion. So the way we're going to approach this is we are going to set up right triangles the same way we did with other types of vector components, like we did for velocity vectors and acceleration vectors. We're going to draw the right triangle to figure out the part of the force that's along the line of motion. And then we're going to use Q's to figure out the sign of those components. So first, we're going to use right triangles to find the component of the force that's along the line of motion. And then, since along our line of motion, we always have to choose a positive direction and then, a corresponding negative direction. We're going to figure out the sign of this component by saying if the force is within, less than 90 degrees from the positive direction, then the force component we get is positive. And on the other hand, if the force is greater than 90 degrees from the positive direction, then the force component is going to be negative. Okay? And so let's just start going through some examples. So first of all, let's say that we have a mass of 3 kilograms that's rolling, free to roll along a horizontal surface. And let's say we have a 2 Newton force over here, and over here we have a 5 Newton force that's acting at an angle of 30 degrees from horizontal. And we want to calculate the acceleration of this cart. Well, always with Newton's second law, you're going to start with a free body diagram. We have a weight force of 3 times 9. So that's 29.4 newtons down. And we have a pushing force from the surface. So that's the normal force. And we have a 2 Newton force over there. I guess I usually don't put in newtons in the free body diagram. And then over here, we have this force of 5 newtons. So this is 2. Okay, so the one that is not in line completely, that's not parallel or perpendicular to the line of motion, and I'm going to choose my positive direction to be this way. You can do this problem with the positive direction. You know, any problem, you get to choose the positive direction. But what I'm going to do is, for this one that's not parallel or perpendicular to the line of motion, I'm going to set up a right triangle. Okay. And this angle here is 30 degrees. This hypotenuse is 5. And now we've broken this up into parts that are perpendicular and parallel to the line of motion. The one that, so this vertical leg of the right triangle is not going to show up in Newton's second law. The horizontal leg is going to. So we have to figure out the length of that horizontal leg. So Newton's second law is going to have, we have the 2 in the positive direction. The horizontal leg of this 5 Newton force is, the magnitude is going to be 5 times the cosine of 30 degrees. And we have to figure out whether it's going to be positive or negative. Well, notice that that 5 Newton force is more than 90 degrees away from the positive direction. If you put the tails of those 2 arrows together and used a protractor, it would be 150 degrees. And so that says that this is going to be negative according to this rule, number 2. And so we have minus 5 times the cosine of 30. The weight and the normal force don't show up because those are perpendicular to the line. And this is equal to the mass times the acceleration. So we have 2 minus 4.33 is equal to 3a. And that comes out to negative 2.33 is equal to 3a. Divide both sides by 3, and you get that a is equal to negative 0.78 meters per second squared. Well, now that negative just is compared to what you chose as your positive and negative directions. So this is the opposite of that positive direction since it's negative, and so the acceleration is this way with a magnitude of 0.78 meters per second squared. One way that this shows up pretty often is for objects that are rolling or sliding along surfaces that are not horizontal. So let's see how it works in that case. So let's say we have an incline of 30 degrees. And we have an object rolling on this incline. And it turns out that for calculating the acceleration of this object, it's not going to matter what the mass is. And I'm going to show you why that is. But let's just say that it has a mass m, and we want to calculate the acceleration of this object. Like always, I'm going to start with a free body diagram. And I'm going to choose my positive direction to be this way. The force is acting on this. There's a weight that's acting straight down. And this weight is the mass times 9.8 meters per second squared. So I'm just going to write this as 9.8 m. Now, if you're looking for other places where the surroundings contact this body, all there is a pushing force from the ground. So that's all the forces acting. And we're going to break up this weight force into a part that's perpendicular to the line of motion and a part that's parallel. So that's a right triangle. This angle is 30 degrees. This 9.8 m is the magnitude of the hypotenuse. And the part of this that's going to go into Newton's second law is the part that's parallel to the surface. So that's going to be the part that has a magnitude of 9.8 m times the sine of 30 degrees. And we have to think about the sine of this component. To do that, think about whether this weight force, 9.8 m, is less than 90 degrees or more than 90 degrees from the positive direction. In this case, it's less than 90 degrees. It's within 90 degrees. So this is going to be a positive component. So now we'll go to Newton's second law. The n doesn't show up because it's perpendicular. And so the only force we have is the positive 9.8 m times the sine of 30 degrees. And that's equal to the mass times the acceleration. 9.8 times sine of 30 degrees is 4.9. So we have 4.9 times m is equal to m times a. And now this is where you can see that the mass doesn't matter, because no matter what it is, it cancels out. You have m multiplied on both sides. And so we get that a is equal to positive 4.9 meters per second squared. The positive means it's in that direction that we chose as our positive. So this is an acceleration down the ramp of 4.9 meters per second squared. Let's do one now where we have two bodies that are on an incline. Let's make this incline 10 degrees. And we'll have two of these bodies in contact. Let's say that this one has a mass of 3 kilograms. This one has a mass of 1 kilogram. And let's say that there's a force applied on the left of 10 newtons. And for this one, let's say we want to calculate two things. We want to calculate the acceleration of the system. And second, we want to calculate the force applied to the 1 kilogram by the 3 kilograms. As always with these, we're going to start by isolating the whole system. So our free body diagram of the whole system looks like this. So there's the 3 kilogram. There's the 1 kilogram. We have a weight force down. Somebody asked me in about a video where sometimes I did the weight as the weight of the 3 on that side and the weight of the 1 on the other side, and sometimes I combine the masses and do a single one. It doesn't matter which one you do. They both add up the same in either case. I guess here I'm going to do I'm going to combine, add the two masses, and then just do it as a single weight force that's equal to 4 kilograms times 9.8. So that's going to be 39.2 newtons down. And then there's going to be a pushing force here. I'll call that N3. And a pushing force here. I'll call that N1. The only other force is the 10 newtons that's applied here. And I'm going to choose my positive direction this way. Now, 3 of these 4 forces are either perpendicular or parallel to the line of motion. So those are easy to deal with. The one that sort of this lecture is about is this one, because it's not parallel or perpendicular to that line of motion. This angle is 10 degrees. The hypotenuse here is 39.2. And the component that is going to go into Newton's second law is the one that's parallel to the line of motion. So the one that's perpendicular to what I've drawn is that positive. That's not going to show up. We have to think about the sign. And you can see that this weight force is more than 90 degrees from that positive direction. And that means that this is going to be negative. So when we go to Newton's second law, we have a 10 that's in the direction of the positive. And we have the negative because of the greater than 90 degree angle. 39.2 times the sine of 10 degrees. We're using, whether you use cosine and sine just all depends on SOHCAHTOA. which leg of that triangle you're trying to come up with. And this is all equal to the mass of the system times the acceleration of the system. So if you multiply out that expression, you get 10 minus 6.81 is equal to 4a. And so that is 3.19 is equal to 4a. Divide both sides by 4, and you get that a is equal to positive 0.80 meters per second squared. The positive says it's in the direction we chose as positive, so 0.80 meters per second squared up the ramp. Okay, so that's the first thing we wanted to calculate, was that acceleration. And now we're going to use that acceleration in our calculation of the force applied to the 1 kilogram body. So for part B, I'm going to draw a free body diagram of the 1 kilogram body. We have a weight force with a magnitude of 1 times 9.8, so this is 9.8 newtons. We have a normal force N1. And then the only other place where there's contact with the boundary of this body by the surroundings is where the 3 kilogram cart is pushing on it. The rules of a pushing force say toward the chosen body, perpendicular to the surface of contact, and I'll call that R for the reaction force. I'm still using the same positive direction. So I'll break this up using a right triangle. This angle is 10 degrees. The component we want, this weight force, just like the combined weight force, is more than 90 degrees from the positive direction. So Newton's second law says R minus 9.8 times, not the cosine, the sine, SOHCAHTOA, the n doesn't show up, and this is equal to the mass times the acceleration, which was positive 0.80. So we get that R minus 1.70 is equal to 0.80. And so R is equal to 2.50 newtons. That's positive. That's I guess this is always going to come out to be a positive number if you've drawn your directions right. So the direction is just going to be the direction of that force vector that you've drawn here. So this is, in this case, in the case of the forces, it's not just that this force it's not that it's positive and so it's in our positive direction. It depends on the way that you've drawn this arrow, and that can be either way depending on the problem. So what we have is in the direction that we've drawn that R vector here, and the magnitude is 2.50 newtons. For the last example, let's do one where, okay, so I'm going to do the ramp this way. The angle here is 20 degrees. And there's a pulley connecting two bodies by a cable. And let's say we have a rolling mass of 2 kilograms, and the cable connects it to a hanging mass of 1 kilogram. And we want to figure out the acceleration of the system, and second, the tension in that cable. As always, I'm going to start by isolating the whole system, and then I'm going to use what I find to get that cable tension. And I'm going to use, for everything, I'm going to use a positive direction to be down the ramp. Okay, so first I'm going to start with a free body diagram of the whole system. And for problems with pulleys like this, remember that all a pulley does is change the direction of that cable force. And so you can always do these problems by just imagining that cable straight. So just rotate this body so that the cable's straight, and you have to rotate any forces as you do it. So for the free body diagram, so there are the two bodies. If you straighten out that cable, we have a weight force down of 2 times 9.8, so this is 19.6 newtons. And you have a pushing force from the ground, that's N. And the weight force, since we straightened out this cable, is now in the direction of motion. And that's 1 times 9.8, so 9.8 newtons that way. We're just using a component of this 19.6 Newton weight force. And so we're going to use trigonometry to figure out what that leg is that's of that triangle that's parallel, that's along the surface of rolling. Our positive is down the ramp. So that means that that weight force is negative. So we have negative 9.8. You can see that this weight force of 19.6 is within 90 degrees, less than 90 degrees from our positive direction. And so that means that's going to be positive. And it's 19.6 times the sine of 20 degrees. And that is equal to the mass of the whole system, which is 3 kilograms times A. So this is 9.8 plus 6.70, and that's equal to 3A. So the left side comes out to a value of negative 3.10, and that's equal to 3A. And so A is equal to negative 1.03 meters per second squared. Our positive is down the ramp, so this negative tells us that this acceleration is up the ramp with a magnitude of 1.03 meters per second squared. Okay, so the whole system, the 1 kilogram is accelerating down, the 2 kilogram is accelerating up the ramp. Like that hanging mass is kind of winning this tug of war. So that's the first part, and now we're going to use that acceleration to calculate the cable tension. To calculate the cable tension, you can isolate either one of these two masses. I guess I'm going to do the simpler one, the 1 kilogram. And if you do the mass that you've rotated, you just need to keep it rotated. So I'm going to do this as a mass like that. There's a weight force acting of 9.8. There's a cable tension acting that way because that's a pulling force, and the rule for pulling force is parallel to the cable, away from the body. Our positive is down the ramp in the direction of that T. So Newton's second law says negative 9.8 plus T is equal to the mass times the acceleration. And remember to use the correct sign in that acceleration, so negative 1.03. So you have negative 9.8 plus T is equal to negative 1.03. And so T is equal to 8.77 newtons. Remember that cable tensions are just the magnitude of that pulling force, and so those are always going to be positive, and you don't have to give a direction for that.